introduction, and thank you everyone for logging in. Well, Ina said this is about Venus today, and I hope you will enjoy this theme. I'm a geodynamicist, and so the perspective is a bit biased towards interior processes and solid state stuff, not so much of the atmosphere, although I will mention it. Yeah, so let's get into it. So these are two bodies you are all familiar with, the Earth and Venus. Well, they're more or less similar when you think about radius, mean density, and gravity. But they look very different when you have a closer look. Like the Earth has plate tectonics, as we all know, and Venus does not have it. So why is that? That's one of the motivating questions of my interest looking into Venus and of many other people too. So still you could ask why, who cares about Venus? So there are many answers to this question, but one is shown here or indicated here. So Venus is a planet that was once in the habitable zone around the sun, so where liquid water could be present on the surface because the sun was a bit cooler. Now it is not anymore, but the Earth is into it. So there's kind of a shift from Earth to Venus, or the other way around, in terms of habitability. So one motivating question could be, is that important, and why? So is, for example, plate tectonics necessary to maintain habitability or something? Also, there have been arguments that the recent tectonics and volcanics that we see on Venus may be similar to the early Earth. So understanding Venus today may inform us about the Earth's hidden past. So this is kind of another motivation to look at Venus. Okay, so the outline of this talk is basically shown here in 5 bullet points. I will try to get you on the same page in terms of exploration and observation of Venus for some minutes. As I said, I'm an interior geodynamicist, so there will be a lot of talking about planetary tectonic regimes, and you will hopefully get to know what that is in a few minutes, and I will explain some details there. Then the third part is, okay, what could be the current of these regimes on Venus, and then some words on how this may have evolved through time, and then there's a brief synthesis and an outlook to future Venus missions. So Venus exploration is as old as planetary exploration itself, which basically started in the 1960s. And here's a very simple statistics where you see the decades. And so time goes from top to bottom. And you can see how many missions were started or planned to go to Venus. You can see it peaked in the 1960s. But there was a problem, because many of these missions had just failed during launch. Fortunately, this got resolved relatively quickly, so the number of failures decreased, which is good news. The bad news is that the number of missions also went down quite quickly. So there's almost nothing here in the 1990s and 2000s, especially when you compare it to Mars, for example. So the interest faded a little bit. Anyway, here are a few images of spacecrafts that delivered some milestones. So Mariner 2 was the first one, first flyby. Then we had the first atmospheric entry 5 years later. Venera 8 of the Russian space agency was the first soft landing on Venus. And here Venera 9 from 1975 is one of the first images from the surface. And also one of the few we have, so there's not much better than this. Obviously, it's easier to look at the atmosphere than into the interior, which you can actually do in some parts from the Earth. And we know that the atmosphere of Venus is really massive, and it's in composition very different to the Earth's atmosphere because it's CO2 dominated, almost, not quite, but almost 100%. And then there's a little bit of nitrogen as well. The surface conditions are kind of very hostile, which makes it very difficult for any spacecraft to land there and stay living for a significant amount of time. So it's about 740 Kelvin at the surface, and the pressure is 93 bars. So much higher pressure and temperature than on the Earth. So this is a kind of cross section through the atmosphere. We have thick clouds at some altitude, which kind of inhibit us to look onto the surface directly from orbit with visible light. We have to do it via radar, but at least that's what we can do. And you can see that there's quite some other compounds than carbon, CO2 and nitrogen. There's also some traces of water, also modified water where one of the hydrogen atoms is replaced by deuterium. I will come back to that a little bit later, and some other things. Okay, this is just a brief introduction to the atmosphere. I will get back to it towards the end. So the surface is obviously the window for us to look into the interior. And since we cannot look at it directly with visible light, it's a bit more difficult to study, but at least we can use radar and other stuff to look at it. And we know that there are quite some volcanic features. So 3 classes if you want. You have small volcanoes, small edifices. You have steep-sided domes that are kind of tens of kilometers in diameter. And you have large shield volcanoes that can be several hundreds of kilometers in diameter. So a wide variety. You also have long lava flow channels. Some of them are called canali, and they can be hundreds or even thousands of kilometers long, which means the lava can actually move significant lateral distances. So here's the distribution of these intermediate and large volcanoes on the surface of Venus. Red are the large ones, and the light blue is the intermediate ones. We don't really know for sure which ones are active, and if any of those are active at present day. But one thing you can see is that there's not like a distribution we have on Earth where most of the volcanoes are located at the plate boundaries. It looks like, well, maybe not random, but definitely not aligned on plate boundaries. So that gives us an idea that Venus loses its interior heat in a different way than Earth. Some of the volcanoes have been suggested as hotspots. Probably remember from the Earth that hotspots are thought to be sourced by mantle plumes that come all the way up from the core mantle boundary. And so these are the most likely candidates for recent volcanic activity. Here's one, Idle Mons, located more or less here. And these kind of hotspots, they show a higher thermal emissivity as measured from Venus Express and the surrounding regions. And so Venus Express has good coverage of the surface, not everywhere, but in many places, and 9 of these hotspots have been identified. So these are really all that would tell us perhaps how many mantle plumes we have inside Venus and where they are located. But it's debated, of course. There are also corona. So these are these circular structures we see in many places on Venus. They have a volcanic or volcano-tectonic origin and very diverse morphologies, which could mean that they have very non-unique formation mechanisms, even though most of these mechanisms consider somehow a plume that interacts with the lithosphere. But it has also been suggested that the different morphologies are just an expression of different stages these coronas are in during their formation. So some may display a very early stage of their evolution. So these are the red ones on the map, while others are in a late stage of their evolution. It's bright violet dots on the surface. And so people have tried to cluster them on the surface, and some regions only contain active ones, and other regions contain mostly these inactive ones. So maybe that tells us something about the thermal state or the structure of the upper mantle and crust as well. Of course, there's also tectonics. There's no plate tectonics, but there are plenty of images on the net you can find where you see like different patterns of ridges and rift zones. For example, here on the left, rift zones, or these groove belts where you have a lot of extensional structures that are very densely packed. And so there is tectonics on Venus, or has been tectonics on Venus, It's just not plate tectonics. So we want to understand why is that difference. One peculiar thing is, or are these tessera, which cover about 8% of the surface, shown here in red on the map. So they kind of occur in many places, and they are very heavily deformed. So when you look at this radar image, you can see a lot of different deformation patterns that overlie each other, and so it's heavily deformed, and they usually have a high topography. And some ideas have been proposed that they have different compositions than most of the other regions on Venus, which are dominantly basaltic. So it could be that these are more felsic in composition. It's not known yet, but that could mean something for their formation history, which is yet unclear. So it could mean that there have been water when the tessera formed, but it has to be confirmed by future missions. There's also been proposed that these are the oldest regions on Venus, which would mean that they could provide windows into the deeper past than other features allow us. And the last introductory thing is the craters I want to show here. So this is a map of all the, not all, but the major craters we have on Venus. It's about 1,000, which is not very much when you compare it to the Moon or Mercury or Mars. And they are spatially more or less randomly distributed, which on the global scale would mean the surface has a more or less uniform age, because the crater density per unit area is a proxy for age. And since the density of craters is kind of low, it will also mean that the surface age is relatively young. So resurfacing must have occurred sometime and somehow. Here's also an image of the largest crater we know of on Venus. It's called MET. It's about 270 kilometers across in diameter, and it has this kind of different ring structures, which I will get back to later as well. So I said globally the surface age is more or less uniform, but people have put quite some effort. I'm sorry, this is a poor resolution image here in the lower left, but people have tried to identify different tectonic and volcanic regions and try to kind of look at the crater densities there and postulate, okay, there are regions that are older or younger than the mean surface age. This is all relative. So this T, 1T is basically the mean surface age, which we don't really know how old it is. So there are postulates that it's as young as 150 million years, but it could also be like up to 1 billion years. We can't really tell. And so most of the timing information we have about Venus is relative. And even on that, there are very large error bars, for example, this one. So it's kind of hard to use the craters for dating different units on Venus. So this is about it, what I wanted to say about the main surface expressions we can more or less easily see. Now I want to get into the interior, which is kind of my home base. So this is very simple sketch, comparison of the Earth and Venus. So we assume there's a core on Venus, there's a mantle, and there's a crust, like we do on Earth. But on Earth, we know from seismology, or for example, how thick is the crust, how thick is the mantle and the core. But on Venus, we don't know that a priori. We don't even know if there is a solid inner core, for example. So why does that matter? Why is it important to understand or study the interior? Because it's very crucial for understanding the whole planet. So here's a little schematic where you can see how everything is connected. So this is the bulk thing here is the mantle, and the mantle and the lithosphere, they basically form one kind of system of the planet, the silicate system, and they belong together. So you cannot really separate them, also including the crust, because the crust is formed by basically volcanism or melting from the mantle. So the mantle cooling, or the temperature in the mantle, really controls how much crust you form via volcanism, and it also controls how much crust you recycle, for example, via subduction on Earth, but also via like downward delamination and dripping of the crust. Volcanism from the mantle through the crust to the surface also determines how much you may outgas to the atmosphere. And again, the recycling of the crust and surface determines how much you may get back into the interior. So it really has a main control on the atmospheric composition. And also when you go to the lower parts of the mantle, it depends on, so if the mantle cools fast, it's easier to get heat out of the core. And if the mantle is hot and stays hot, it's much more difficult to get heat out of the core and cool the core, which is very important for understanding how the core has evolved and if it has a magnetic field or not, which is currently not the case on Venus, and there's no record it has ever been. So the mantle is really key for understanding Venus and its evolution. Okay, how can we know these things about mantle and the core and the interior? So one thing is seismology, of course, which we don't have for Venus, or not in a useful form at least so far. So a simple measure to do it is via the moment of inertia, which is basically a measure for the mass distribution in a rotating body like a planet. It's defined with this simple equation. And what the key point is that even for the same bulk density, two bodies or two planets can have a very different MOI. For example, if it's a homogeneous sphere, or one that has a light mantle and a heavy or metal core. So for the homogeneous sphere, you can easily compute the moment of inertia. It's 0.4 times the mass times the radius squared. And if you have a dense core, this value is smaller. If you would have like a hollow planet, which doesn't make much sense, the value would be larger than this 0.4. You can actually observe MOI from, for example, from the precession rate of the planet's spin axis, which is illustrated here conceptually for the Earth. And you can also do it for Venus, but it's much more difficult because Venus is a very slow rotator. And so there's quite some uncertainty on this measurement. So it's 7% uncertainty. And when you compare this to Mars or Moon, this is much larger. So this is a relatively recent study by Margot et al., where they tried to do that, and they get this distribution, and you can see the mean of this distribution is about 0.337, which is not too different from the Earth, but the uncertainty is quite large. Anyway, it's smaller than 0.4, which tells us, okay, there should be some sort of dense core inside Venus. But we don't really know how big it is. And this is shown here. It's another study where they try to kind of separate the interior of Venus into different layers, an upper mantle, lower mantle, outer core, inner core, and a crust, I think, and assume several densities and compositions for these layers and made Monte Carlo simulations of these planets and computed what the moment of inertia would be as indicated here by color. And I don't want to go into detail here, but what you can see is that there is a huge uncertainty. For example, the radius of the core mantle boundary of the outer core has an uncertainty of about 1,400 kilometers, between 3,000 and more than 4,000 kilometers. There's no, we cannot really say if there is an inner core or if it's a really large inner core. It could be both. So this measure doesn't exclude all the possibilities. The temperature at the core mantle boundary may vary by 2,000 Kelvin from doing this exercise. And also the upper mantle may be as cold as the Earth's mantle, or maybe much hotter. So there's a huge uncertainty in this, which is, kind of a bit sad. But we are working on it. And of course, these different temperatures, they reflect back into material properties like viscosity. If it's hotter, it may be less viscous, and if it's colder, then it may be higher viscosity, which then is very important for heat transfer and cooling of the planet. So let's get around this kind of thing that we don't know how thick the mantle is, and let's assume some mantle geometry and a bulk composition. How would the mantle behave at present and back in time? And this is when these regimes come into play. So plate tectonics is one regime, one particular regime, but there are others. And ideally, we want to characterize a planet with one of these regimes, and in the best case, throughout its entire history, but this normally does not work. So what are these regimes? You can define them in terms of the mobility of the lithosphere, which is basically, if the lithosphere is moving, or it's kind of stagnant and not moving. You can also do this in terms of surface heat loss mechanism, which is shown here. So for the Earth, you have plate tectonics. Some people name it the mobile lid, although it's not quite the same. And their subduction is the dominant player, right? So because you have subduction, heat transfer is quite efficient. On bodies like Moon or Mercury or Mars, you have a stagnant lid. That's a one-plate planet, and the heat transfer here is much poorer than for the Earth, so, because everything happens via conduction through the lithosphere. And you have a third mode, which is the heat pipe, where you have a lot of volcanism that kind of gets the heat out of the interior. So a huge density of volcanoes, and Jupiter's moon Io is an example for this. So the question is, where is Venus on this diagram? And this is the main part of this presentation, actually. So I briefly want to get you on the same page in terms of these regimes. The mobile lid is where you have significant rates of horizontal surface motion. You have tectonic resurfacing, you have subduction and recycling. The heat loss for the surface is relatively efficient, which means you cool the interior quite efficiently, and you have a strong coupling between the surface and the interior. Because you have this kind of cold viscous slabs going down into the mantle, you have a strong heterogeneity in terms of temperature and viscosity and density in the interior, which you can, for example, see in gravity data. Once again, mobile lid and plate tectonics is not quite the same. Plate tectonics regime we have on Earth is a sub-regime of the mobile lid, which has a very highly localized deformation and plate boundaries, like ridges and subduction trenches. The other member is the stagnant lid, where this horizontal surface motion is basically zero or negligible. So that means that resurfacing is very inefficient. If you have some, it usually happens via volcanism, but that's not mandatory in a way. So the heat loss through the surface is poor of that. It's poor because of that, and it happens via conduction only. And usually the interior is supposed to be hotter. And the interior is also decoupled from the surface. On the other hand, you have much less lateral heterogeneity in the mantle because you don't have subduction and only these delamination or drips from the lithosphere that go into the deeper interior. Mars, Moon, Mercury may be some examples of this. The heat pipe is actually not too different from the stagnant lid, except that you have much more volcanic activity piercing through the crust and giving very extreme heat loss via volcanism. But still, you don't have subduction here, and the recycling of the crust happens only via delamination, not via subduction, so it's kind of inefficient. There's a fourth regime, which has recently been suggested. It's the squishy lid, which is indicated here. So you have also dripping and delamination of the lithosphere that kind of sinks down into the deeper interior, that induces a return flow, which contains partially molten material, which then is yellow stuff here, which then intrudes the crust at some depths usually and makes it weak, because the melt is weak and stays there for some time, and kind of have weak zones in the crust and lithosphere and make it weak, and that kind of makes it easier to make these new plate boundaries, which are a bit different than the ones on plate tectonics. They are more ephemeral, but still they mobilize the lithosphere. So these arrows here, they indicate that things are moving, but not as coherent like the Pacific plate, for example, very large plate on the Earth. This is not what happens in the squishy lid, where the plates are much smaller. Anyway, this keeps the crust thin, and that on the other hand, increases the surface heat flux. So it could be a candidate, or it could be a regime that was relevant for the early Earth, or maybe even present Venus. Here a brief point that regimes do not stay constant through time. So here's a simulation I made a few years ago, which was in a stagnant lit regime in the beginning. So the mantle heated up, as you can see on the top. And then at some point, because mantle convection got more vigorous when you heat up, and lithosphere becomes thinner and you have more magmatism and volcanism, you trigger some sort of episodes of mobilization of the surface, where the model was in the mobile lit for some time until this triggering shut off and you're back in the stagnant lit. So you can have these episodes where, for example, the heat flux through the surface is much higher. So this is a time-dependent regime with episodicity. But one thing we have to keep in mind is that questions like how often do these occur on either global or regional, how long do they take, do they leave anything behind on the surface? This is very important if you want to relate this kind of regimes to Venus surface record. So when you really want to get into the details and look at, okay, what regimes are feasible for a given planet, models become really powerful to identify those feasible regimes. Of course, you have to assume some conditions and parameters, actually quite a few. But here's one example. And it's a regime diagram that shows the strengths of the lithosphere basically on the x-axis, and on the y-axis is the magmatic eruption efficiency. So basically, how much of the magma goes from the interior up to the surface, and in simple words, forms a volcano. And so each of these dots is one of these models, a 2D model where you have temperature distribution and also composition. So the color of each dot indicates one of these regimes I was introducing to you. And you can see for a very weak lithosphere, which is here, you get a mobile lit like the Earth. But as soon as you have a stronger lithosphere, you end up in another regime, either the episodic behavior or the stagnant behavior or this plutonic squishy behavior the last regime I was talking about. So the question is, of course, where is Venus on this diagram? And when was it in this location? And this is hard to pin down. So there are some proposals that for the Earth, the eruption efficiency of magma is between 10 and 20%, but that's also debated. And even if you assume that this is the same for Venus, we could still be along this array here in terms of yield stresses, because we don't know how strong the lithospheres are. We do know that the Earth's lithosphere is in a mobile lit mode, so an effective strength that should be quite small. But Venus, we don't know. But if it was in a state where the lithosphere is somewhat stronger, it could end up in this squishy lit mode. So why should it be stronger? Perhaps because it was drier, or is drier, and has less water inside the rocks, because dry rocks tend to be stronger than wet rocks. On the other hand, we know that Venus lithosphere is kind of very hot. The surface is hot, so that propagates into the interior. So warmer rocks are usually weaker than colder rocks. So that's kind of opposing this kind of idea. And you can see it, for example, here in this Christmas tree diagram, where this kind of turquoise is the strength profile of an oceanic plate, and is actually stronger than what these people suggest for Venus lithosphere. So it's not so easy to really place any planet on these regime diagrams. Plus, you have the problem that this is just two parameters here, yield stress and eruption efficiency. But you have about, I don't know how many, but it's quite a few of these parameters that can completely change where these diagrams are. So you can quickly assess that by looking at a relation between the strain rate equation, which we know from the lab. It depends on temperature and pressure, on various material parameters, depends on water content, grain size. stresses, different deformation mechanisms. So there's a lot of things you have to map out, and this is not even all of it. And honestly, much of this has not been mapped out yet. So we need to do this better, and there's work to do here. Anyway, let's try to narrow it down for Venus. Here are these 4 regimes I was introducing before. And well, we do know there's no coherent plate motion on Earth or on Venus today. There's no active subduction. So we can exclude this mobile lit mode for today. Well, there is perhaps some volcanism if you believe in this hotspot hypothesis that there was recently, but it's relatively limited. So there were not so many of these volcanoes distributed on Venus. So this heat pipe regime appears quite unlikely. We should have much more of these volcanoes being active. So let's exclude this too. So you have the stagnant lid left, you have the squishy lid left, and also this episodic kind of behavior. So to do more, you want to look at some data for Venus. So here's topography and gravity or Geo.X at the surface. The topography is actually, has a range between 2 and 7 kilometers, but most of it is kind of relatively low amplitude topography. And one thing you can see when you compare these two maps is that the highs in the Geo.X can correlate well with the highs in the topography, which is very different to what we have on Earth. So that's something we should look into it. Often it's a bit more convenient to take these maps and convert them into spectral space via spherical harmonic decomposition. And so here are the two for topography, no, for gravity, sorry, for Earth in blue and Venus in red. And let's ignore this kind of part on the right here, which is smaller scale stuff. Let's focus on the longer wavelengths. And you can see there are some differences in the spectra. So the blue one, the Earth one, kind of decreases faster at long wavelengths, which is here, than Venus. And one other feature is that the correlation between topography and Geo.X for long wavelengths is very poor for the Earth. Like here, it's basically 0, but it's very high for Venus. So how can you use that information in terms of modeling? So this is a model I made a while ago, and I used some different parameters here and that end up in a different viscosity profile of the mantle. So you have 4 models in different colors, and these are the viscosity profiles. And when you predict the power spectrum of gravity for these models, you get up with very different results. This is logarithmic, by the way, and the black bold curve is for observed Venus. And you can see some models do much better, while others, this kind of greenish one, does very badly. And you can also do this for the correlation between gravity and topography here on the right, but it's less conclusive for these 4 models at least. But here you would kind of take the red bold curve as maybe the best viscosity profile for present Venus mantle. On Earth, we know that there is a jump in, or like a discontinuity in viscosity at the upper lower mantle boundary. And I tried some of these contrasts as well, but when you include that, you can see that here on the right, the correlation between gravity and topography, it breaks down for long wavelengths, which is exactly what we see on Earth, but we don't want it for Venus. So it could be an indication that we don't have this contrast between the upper and the lower mantle on Venus, and could be an indication that we have different distribution of water content in the upper and lower mantle compared to the Earth. And in fact, we probably don't have an asthenosphere inside Venus. You can also look at these models in terms of the number of plumes. So this is simple plume tracking. This is for different depths of one model. I think it's the red model, the S2. You can count these basically through time also, and compare this to the number of anomalies in terms of thermal emissivity Venus identified on the surface. So these were 9, there may be more, but these are the ones confirmed. And if you believe in that, then these two models would do quite good job. So the red one and the dark red one, while the others not so much. So we can narrow down how the mantle should look like in present day in terms of viscosity, which is something very useful to understand the planet and its evolution. You can also look at crustal thickness. So it's the same model predicting some crustal thickness in terms of a mean, and what you can see is that this is kind of very massive. I mean, all the constraints, not constraints, but estimates we have from other techniques are down here. So basically this dark black is a recent one from James et al. Like 10 or 20 kilometers. And the stagnant lid model gets like 120 or whatever that is. So way too much. I tried some other parameters, but you never get down to these values. So it is typical for these stagnant lid models. You always over-predict the crustal thickness because they stay too hot and produce too much magma in volcanism, so that you get too thick crust. So it's not really supporting this stagnant lid. Here's a comparison for different regimes. It's not from models I made myself, but I compiled the data. So you have the heat pipe, you have the stagnant, you have mobile, squishy, and episodic regimes. And here again, you can see the kind of estimates from gravity and topography inversion. So you see that heat pipe and stagnant don't do well. Episodic could do well if you are kind of in a time where a resurfacing episode just happened not too long ago. The squishy lid definitely reduces crustal thickness, so it may work if you find a good parameter set here or something. And the mobile lid obviously produces a very thin crust like we have on this. So again, not really in support of the heat pipe and the stagnant lid regime. What about heat flux? Well, this is not an observable, but you can kind of get it from topography. You can fit topographic profiles and then use an analytic flexure model to convert this into elastic thickness. And from elastic thickness, you can infer a heat flux, which has been done here for many places on Venus, in particular Corona. And then they compile a map where some locations have very high heat flux. For example, these crosses and circles, they indicate Earth-like values of heat fluxes. So how is that possible without having a mobile lid regime? When you look at models like the ones I showed before, in a stagnant lid, no, you get like 20 on average, and then also the spatial variations are very small. So too low heat flux. In the episodic model, yes, you can get times where you have extremely high heat flux, like 200 milliwatts per square meter in places. But this works in terms of heat flux, but you would need to have a surface that is moving quite fast in places, which is not observed, so it doesn't work. You can also think about the interior mass distribution. We have talked about it before, but from topography and gravity, you can also get a bit more information than these 1D profiles. You can get the center of figure and the center of mass. And for Venus, we know that they are kind of very close together. So the offset between them is very small. So what does it mean is that there should be no hemispheric scale mass heterogeneity inside Venus. But when you have an episodic model where you have very catastrophic subduction that propagates from one place over the planet, you would predict just that. So here's another model from King where these overturns or episodes occur, and you can see the center of mass, center of figure offset. It really shoots up to very high values. The observed one for Venus is down here, and you never get to this. But it's very time dependent. This is because what is shown here, you can see, now this is the density anomaly atop the core mantle boundary. When you initiate an overturn and you subduct crustal material that is sort of denser basalt, at some point you hit the core metal boundary and create a density anomaly there, and then it spreads laterally until it makes a hemispheric density heterogeneity. So here you would have a very high offset between the center of figure and the center of mass. You will be at this peak. But then soon after, you mix this basically, and you don't have a hemispheric scale heterogeneity anymore, but it's kind of globally distributed. And then you would get down to this kind of small value. But when you look at the time here, this is like almost 1 billion years. So it's kind of long. And what it means is that this peak cannot be anywhere close to where we are on Venus now. So this must be like many hundreds of millions of years ago, at least on Venus, so that this overturn mechanism would still be in line with what we see on Venus today. But when you think then about the heat flux again, this would be very small here and it wouldn't work. So in the end, we probably have to say this episodic lid is not so straightforward to squeeze into Venus evolution. And that's just the same for the stagnant lid. We cannot get the heat fluxes right and so on. So we're kind of left with this option for the moment. So let's have a quick look. So as I said before, this is a kind of recent regime and it's much less investigated than the other regime. But here's a compilation of the heat flux predicted by this kind of regime. So look for the triangles, downward pointing triangles, and compare it to the squares, which is the stagnant lid. And what you can see is that the average heat flux across the surface is at least a factor of 2 or 3 higher than in the stagnant lid. So it's much easier to get like target values like the ones proposed from this kind of method here and with the topographic flexure. So that's good. And another thing is shown here. So recently it has been proposed that you have some sort of small regions on the surface of Venus called campi that are like mobile crustal blocks that move like or have moved like just like pack ice. So they are kind of in a way comparable to the Earth's tectonic plates in terms of how they move, but they're much, much smaller. So tens of kilometers compared to thousands of kilometers. Could indicate some sort of rather local style rather than global style tectonic motion. Well, this would fit well with the squishy lid dynamics, which predicts that these plates will form are much smaller than what we have on Earth. So like hundreds or maybe tens of kilometers. So if we believe in these two arguments, then the squishy lid is a good option for present-day Venus. So you would place Venus right here. So heat transfer is definitely a lot of conduction, but there is some sort of lithospheric mobility. So you don't get into this corner, but somewhere 1/3 this way. And the same is true for volcanism. So there might be some volcanism, but not the dominant mode. So you're up here. So what about the past? I think I have to rush a little bit. So you want to go back in time. And of course, you can only go back in time for what is recorded on the surface here, tectonic or volcanic markers. So that's some hundreds of millions of years. And there's little you can do, but some things have been done. You can, for example, look at these craters and sorry, the circles here are a bit shifted. So there's 2 rings for this mat basin, which I've shown before. And so people have tried with impact crater formation models to get this morphology with 2 rings. And without diving into details here, some models do well and some do not. And the ones that do well are usually those who predict a very small heat flux from the interior to the atmosphere. So a low value of the heat flux, they postulate about 28 milliwatts per square meter, would be indicative of a stagnant lid for the time when this crater formed, so like 300 million years ago. But it could also be that this crater was just in a place where heat flux was low for some other reason, while it was high in other places. Against this kind of argument for a stagnant lid, or some other arguments, for example, when you look at this kind of region here in the upper left, Terra. You can look at topography, and there's a lot of convergence recorded in the topography and in the relief. So, and it has been suggested this is because of kind of convergence from north to south, and it's probably driven by subduction, which of course includes some sort of surface mobility, at least in this region of Venus. So that's not an argument for stagnant lid. But these mechanisms, they are always debated, and other people or other arguments from the same setting indicate that there has been a plume involved rather than only subduction. So this means that, or like this led to the idea of this mechanism, plume-induced subduction. And it has been proposed to happen on Venus. So basically what that is shown schematically here. You have a plume that rises from the core metal boundary or what, and interacts with the lithosphere, deforms it, maybe creates some cracks, and then you get some sort of lava or magma out. And at some point you induce subduction, that is rolling back. This is a schematic, but it has been seen in geodynamic models. It has also been observed in laboratory experiments, like jelly syrup and stuff. And it seems to be also present in some corona on Venus. It's not so easy to see the details here, but you can see like triple junctions here, similar to what is shown in this numerical model. And so again, it would imply some sort of at least regional surface mobility, so not a global stagnant lid. And it would definitely be easier to get this kind of behavior when you have a weak lithosphere that would be favored by magmatic intrusions. So the squishy lid would again do quite well. So, but anyway, there is some indication that the regime or the surface of Venus was perhaps a bit more mobile in the past than it is today. So you would move Venus by some amount to this corner where the mobile lid is and present day. It's of course not carved in stone, but that's what several people think. And of course, we can play this game further and try to get back further in time, but this is very difficult because there are no archives left for this on the surface. But the atmosphere may contain some clues about this in a cumulative sense, time-integrated sense. Because, for example, it contains argon-40, and this is a byproduct of decay of radiogenic potassium, which comes out to the atmosphere upon melting of the silicate rocks. Venus has relatively little argon, and so one argument is that only a little of it is outgassed from the interior to the atmosphere, which would mean that there has been a relatively limited amount of volcanism and crustal production over time. But that's all you can say so far. I also mentioned this, that some of the water or like water vapor in Venus atmosphere is actually not made of two normal hydrogen atoms, but there's at least one of these deuterium atoms which have one neutron, and this is heavier, so it's a bit more difficult to get this out or let it escape from the atmosphere to space, which is the reason why, could be the reason why this ratio of D to H is very high in Venus atmosphere. And it could mean that there was much more of the H in the past, which just left to space. So that could mean that there are different surface conditions earlier on, and also that there was more abundant water, perhaps also in the interior, which would then, of course, change the rheology of the rocks and the tectonic regime. One of the last things I want to say is that all of this is, of course, coupled. Right? I showed this in the beginning, and so this is something to remember. Planetary evolution is a story of couplings. So mantle temperatures are time dependent. That makes the volcanic outgassing time dependent, makes the atmospheric composition time dependent. This reacts with the surface temperature, and this also feeds back on the tectonic regime, and then goes back to the mantle temperature. So everything is coupled, and I think we should put more effort into this and try to understand these couplings. This is just an example for one model where they try to couple the interior and the the atmosphere. And then, of course, you can try to use your target surface temperature of present day 740 as a target for your model or as a constraint. You can do other things like density of the atmosphere or composition. So that's kind of promising, and I think more should be done in this respect. I think I will drop over this because the time is running out. So this is my synthesis. I hope I convinced you that Venus interior is key to understand this planet and its evolution. There are a number of regimes, and they are very sensitive to many parameters of Venus rocks and the environment in general. And very few of those are really well known for Venus, which is a problem. With the current data we have, it's not so easy to really pin down what regime Venus is in, but the squishy lid is a very promising regime for describing modern Venus. Well, with current data, we are kind of, yeah, it's very difficult to constrain how we evolved to the present day for Venus. Many possibilities remain. Here's just a small compilation of what people have proposed, so that Venus was always in the stagnant lid. It was in the stagnant lid, and it's now in a transition to some sort of mobile lid. It was in the mobile lid before, and it's now in the stagnant lid, so they're kind of opposing each other also. And there have been scenarios, episodes I was talking about. So it's difficult to rule these out. Many of the scenarios fulfill some constraints and fail with others. There's none that really matches with everything. So the only thing that seems to be for sure is that we started off with a magma ocean and will end up with a terminal stagnant lid when everything has cooled down sufficiently. So what we really need is more data. And this is my last slide, I think. And we will get it. So there's a couple of missions, or actually 3 at least missions going to Venus in the next 10, 15 years. And it will deliver us, hopefully, with a lot of new data. For example, we will hopefully know better the radius of the core with an improved accuracy of the moment of inertia. We will get higher resolution gravity and topography, so better constraints on crustal thickness, also on heat flux and recent volcanic activity. There will be more measurements of surface and atmosphere composition. So it's a lot of activity that will hopefully revive our understanding of Venus in the next decade. And with that, I'm stopping here. I hope there's some time left for questions. And if not, just drop me an email or something later on. Also, I want to make you aware of this collection of articles and space science reviews. Much of the thoughts I shared with you today can be found there in one chapter I wrote, but there will be many other chapters added about other aspects of Venus, hopefully soon, and it's all open access, so which is good news. So that's it. Thank you.
Thank you, Tobias. This was a great presentation and very inspiring. I will stop the recording here